Cl2. What would be the enthalpy change of atomization for chlorine? So we know that chlorine, what state do we find it at standard conditions? Gaseous is right. Now, we're going to form from it, by the definition that we have there, we're going to form what? So what the definition says is we're going to form 1 mole of gaseous atoms. So always in the products, we're going to have 1 atom of the whatever species we're talking about. In this case, chlorine. 1 mole of atoms, always in gaseous state. On the left side of our equation, we're always going to have the species in its elemental form and its most stable state at standard conditions, which is Cl2. So how do I finish this equation? What am I missing in this equation? 0.5, 1/2 of a chlorine molecule. So this equation is the standard enthalpy change of atomization for chlorine, okay? We're forming 1 mole of chlorine atoms in gaseous state from chlorine in its standard state, okay? Now let's look at another example. So everybody has this one written down. Let's try something else. What will be the standard enthalpy change of atomization for, let's say, sodium? So by definition, in the products, what are we going to have? Sodium in gaseous state, 1 of them. Now, what are we going to have on the left side of the equation? Sodium in solid state, that's right, metallic sodium. That is what we're going to have on the left side of the equation. So this is how we define enthalpy change of atomization. So you see, for a metal, it's different than for a non-metal because it depends on where we're coming from. This one in standard state is a solid, the other one in standard state is a gas. And that is going to influence the energy. Now, standard enthalpy changes of atomization, do you think they're going to be exothermic or endothermic? Endothermic? What do you think at home? Anybody at home? What do you think? Students at home, what do you think? Can you hear me?
Hello, yes.
Yes? Okay. So is it endothermic or exothermic? So the ladies here in classroom are saying it's endothermic. Do you agree with them?
Yes, it's endothermic.
That's right. It is endothermic. It's an endothermic process because we're going, in this case, in solid sodium to gaseous sodium, we are breaking interactions to form the gaseous state. What interactions do you think we're breaking? Oh, what happened? Okay. What interactions do you think we're breaking here? Just minimize it, Mr. Ramadan. Just minimize it, Mr. Ramadan. Open the browser and just leave this one. Yeah, there we go. Yep. Okay. And can you close the blue banner at the top, please? Thank you. There we go. Okay. So what interactions will we break when we go from sodium solid to sodium gas? What interactions are we breaking? Any ideas?
Intermolecular bonds.
That's right. We're breaking, well, not exactly intermolecular in this case, but we're breaking the bond that keeps the sodium atoms together. And what keeps the sodium atoms together in the solid state is the metallic bond. So we're breaking that metallic interaction, and that's what makes them gaseous. Now, in the chlorine that we had before, chlorine gas, Cl2, is going to turn into chlorine atoms. We're also breaking an interaction there, which is the bond between those 2 chlorine atoms. Of course, half that, because we're only forming 1 mole. But that means that this is always going to be endothermic, always more than 0. Okay, the second equation says electron affinity. Enthalpy change when 1 mole of gaseous atoms acquires 1 mole of electrons from infinity to form 1 mole of gaseous negative atoms. So let's make it with an example. Let's do the example of the enthalpy electron affinity of, for example, fluorine. So fluorine, we're going to have it in one side and on the other side. What are we going to have on the left side? So it says 1 mole of gaseous atoms. So we're going to have what?
Gas. One
Yes,
mole.
fluorine.
Guys,
Yeah, fluorine gas, that's it. Fluorine gas, that's it. And what are we going to have on the right side of the equation?
Fluorine minus. An
Fluorine
ion.
minus, so that means the fluoride ion. And in what state? Gaseous, it says it right there. Yes, so it's
gas,
gaseous too. So what are we missing here? That's right. We need 1 electron. Where? On the left side. This is the enthalpy that we call electron affinity. How much energy is going to be exchanged when we go from the gas atom in gaseous state to the fluoride or whatever element in the negative ion being formed? Is this exothermic or endothermic? Any ideas? What do you think? Just a thought. Maybe you're not right, maybe you're right. Well, I'll tell you myself. This one is mostly exothermic. Mostly exothermic. But not always. Not always it's going to be exothermic. But in the majority of cases, it's exothermic because an electron is being gained. And in most cases, for example, if you can imagine, if fluorine gains that electron, it actually would want to gain that electron. It's in its benefit in some way. So that's why it is exothermic. The next one that we have there is first ionization energy. So what is first ionization energy? That one is very simple. So I'm going to erase the ones that we have here, and let's do first ionization energy. What is first ionization energy? It says it right there. So let's do it for a specific element. Let's say, I don't know, calcium. Calcium. So calcium at both sides. What do I have to write on the left side of the equation?
Calcium gas.
Calcium gas, that's right. Minus an electron. So we can write minus an electron, as you're saying, or we can say on electron at the right side. That's right. That's correct. We can write it like this. So what else are we missing?
Charge. Plus charge.
Charge. Charge where? On the right side. That's
Right
right.
side.
And what else? Gaseous state. So this is the first ionization energy for calcium. Of course, it's the first because we're taking only the first electron away. Is this exothermic or endothermic?
Endothermic.
It is. So you see exo and endo, it's actually endothermic because we're trying to pull something away. Always when we're trying to take something away, most cases it's going to be endothermic because we need to break some sort of interaction. Then we have standard enthalpy change of formation, but we discussed that one last class. Forming a substance from its elements in standard state. So I'm going to skip that one because we already discussed it. And the last one is lattice formation enthalpy. Lattice formation enthalpy says there, the enthalpy change when 1 mole of an ionic substance or ionic crystal lattice is formed from its isolated gaseous atoms. So let's think about an ionic substance. What ionic substance can we talk about? A simple one, of course. Say that again.
Sodium chloride.
Sodium chloride, of course, is the one that we always go to because everybody loves sodium chloride. So NaCl, it's going to be in its ionic crystal lattice, which means in what state?
Solid.
Solid state. Are we seeing it? I don't see it yet. Let me just give me a second. I'm going to have to fix this, that we're not seeing the information. Where is it? Why is it not? There we go. All right. Now, what are we going to have on the left side of this equation?
Sodium cation and chloride anion.
Sodium
In gases.
cation and chloride anion. In what states? Gaseous states. Now, this is the definition of lattice formation enthalpy. And it's called formation, which means that it's the two ions coming together to form sodium chloride in this case. Do you think this is going to be exothermic or endothermic?
Exothermic.
Why exothermic? Why endothermic? If we're forming a bond, is that going to be exo or endo?
Exo.
Exothermic. Bond lattice energies are always exothermic because we're taking something that is very positive, something that is very negative, and we're forming a lattice with them. That is very exothermic. So, the problem with lattice energies is that we cannot measure them in the lab. We cannot. It's impossible. So, because we cannot measure them in the lab, we have to determine them using a cycle, Hess cycle. So that Hess cycle that we use to calculate lattice energies involves all these other enthalpies that we discussed right now. Enthalpy change of atomization, electron affinity, first ionization, standard enthalpy change, all of them. And that cycle itself is called a Born-Haber cycle. So it involves all this information. So this one is coincidentally for sodium chloride. Who would have thought? So for sodium chloride, we have the enthalpies of formation, which are the equations that we form, sublimation, atomization, energy of sodium, first ionization energy, electron affinity, and lattice enthalpy. All of those are the ones that we can find in the books, except for the last one. That's the one that we don't know. Now, we already said that some of them are positive and some of them are negative. Now, one that we didn't discuss, but you can see here, is enthalpy of sublimation. What is the enthalpy of sublimation? That's right. From solid state, it becomes a gas. That is the enthalpy change of sublimation. Now, if you look at the equation for the enthalpy change of sublimation, which is this one, what does it look like? Yeah, it's the same thing as the atomization. It's exactly the same. For a metal specifically, or for a solid, going from the solid state to the gaseous state like this, it's the same thing to say sublimation than to say enthalpy of atomization. It's the same thing because we're doing the same process with a different concept, but we're doing the same process. Same as enthalpy of atomization, we say it here, and we see that it's 1/2 of chlorine gas to form the chlorine gaseous atoms. That is very similar to something that we talked about last class, which is the enthalpy of the bond enthalpy of chlorine. But we're only using half of it because in the previous one is how much energy we need to break the bond between two chlorines. In this case, what we're talking about is how much energy is needed to form 1 mole of chlorine atoms. So the enthalpy of atomization and the bond enthalpy are related, but they're not exactly the same because of the definitions. Keep that in mind. So that means that with all this information and the values that we can find from them that I give you here, we can calculate the Born-Haber cycle for sodium chloride. It's just building a cycle. We want to determine this one that we call 6. 6 is from sodium ions and chloride ions going to sodium chloride. That is our enthalpy or lattice energy. And you see it's exothermic, it goes down. The energy of the products is lower than the energy of the reactants. But we cannot go directly. So we're going to form a path. And the path is going to involve a variety of things. First of all, we know that sodium chloride can be formed from its elements. How do we call that energy? Going from the elements to sodium chloride? Enthalpy of formation. So that enthalpy, we know it, and we know that it's exothermic, so it goes down. So now we have to go the other way around. We have to go all the other way so we get to sodium, to sodium ions and chloride ions. And then we start. First thing we did, what changed in going from here to here? What was the change in this step number 2? Sublimation, that's right. Sodium solid turned into sodium gas. You can call it sublimation or atomization energy. So sodium turned into solid, from solid to gas. Step number 3, atomization of chlorine. That's right. Now both sodium and chlorine are in gaseous state. Now the order doesn't need to be exactly like this. Of course, if you add them, it's going to give you the same value. But of course, you cannot do the next step, which is what? Ions are formed. What ions are we forming in step number 4? First ionization energy of sodium. So that is the step that we go from here. Now, we could do, for example, the atomization of chlorine before the atomization of sodium. We could do that. But of course, we cannot do the ionization of sodium before we turn it into a gas, by definition. Mathematically, it's going to give you the same result. But if you think about it in the chemical way, first you have to turn it into the gas, and then you have to turn it into an ion. And then we have this step, which is the only step that we have, that is exothermic. And what is it? Electron affinity. Now, electron affinity, the first electron affinity of elements is, in most cases, as we told you, exothermic. However, if there's a second or third electron affinities, those are endothermic in most cases. Keep that in mind for other exercises. Now, if we look at that and we're building a Born-Haber cycle and we're building, what we're doing is a Hess cycle. We want to find this energy, but the path that we're going to be taking is this one. So to find number 6, we're going to go 5, 4, 3, 2, 1. Now how they wrote it here, you see it. -5, negative, because we're going in the opposite direction as the arrow is showing. The same as 4, we're going in the opposite direction of the information that we had. The same as 3, the same as 2. The only one that we're going in exactly the same direction is number 1. So that's why the one has a positive sign on it. All the rest are in the opposite direction. And with that, we can find the enthalpy of lattice, or lattice enthalpy of this process. Let me just, if you can take a picture, yes, go ahead. This is lattice enthalpy. Now let's do a calculation of lattice enthalpy, and then we'll see how that goes. So the one that we're going to do, I'm going to skip the second example, which the only difference between the second example, which is magnesium chloride, and sodium chloride, is that the enthalpy of atomization of chlorine has to be counted twice because we need 2 chlorine atoms. That is the only difference that we have there. The same as the electron affinity, because we have 2 chlorine atoms. The other difference is we need a second ionization energy for magnesium because magnesium has to lose 2 electrons. The rest is the same process. We are trying to build the cycle so that we can find number 7 using a different path. It's a Hess cycle. Born-Haber cycle is a specific type of Hess cycle. All right, let's do a calculation. The calculation is this one. I hope you can see it. Fully labeled Born-Haber cycle for the formation of solid barium chloride, BaCl2, from its elements. Include state symbols for all species referenced. So I'm going to try to expand this as much as I can so everybody can see it. Try to build that cycle. We're going to be going on the break in a second. So when you continue doing that calculation, build that cycle. The ladies here will show us what they did. People in your houses, if you can, somebody's writing through the chat, but unfortunately I cannot see the chat at the same time. Sorry, but I'm just checking. Give me a second. Uh, okay, so if you are at home, you can send us a picture if you have your information and we'll check it. So start working on that and we'll come back after a while and we'll start with the rest. Information to keep in mind, barium is from group 2, but you knew this already. Okay, my computer is working now, so people at home can also see me. For some reason, in our screen at school, we cannot see my face. But can you see me? Is my camera working in people at home?
Yes.
Yes.
Okay, good. Sure. Okay, does anybody have an answer for us? At home, can you send us an answer or a picture or something? If somebody has an example of a diagram, we can see it, we can broadcast it for everybody. If anybody can send it to through the chat window, or if anybody here has one, anybody? How are you doing, ladies? What do you have? Amira? Ayana, not yet. Aziel, how are you doing? You did the calculation. You have a value? How much? Minus 573. So we have minus 173. We have one. I don't know if that's correct, actually, but that's the first answer we have. So let's see if somebody agrees with Aziel's value of minus 573. How are you doing, Camila? What about people at home? Does anybody have an answer? Minus 573. That sound right? Anybody have something similar? That so far is the only answer we have. Upon 173, you have it? So we have confirmation. Minus 573 it is. So let's just very quickly show the answer. First, we're going to show Asiel's answer. If I can, I'm going to try. So here's Asiel's calculation for everybody. Let's see. Give me a second. How can I do this? Let's see. Here we go. I think it's going to work. Let's see. Why can I show it?
Mr. Daniel,
Yeah.
what was the answer?
I'm going to show you in a second. But that's not working. Wait a second. Stop. I need to share photo, I guess. Share video. Share video. Here we go. There we go. So the answer, this is Azel's answer, is minus 573.
I think it's correct.
Yep, I think we agree.
I get the same one.
Okay, let's see. Another answer. Okay, we want to check it again. Let's check it again. Take a photo, somebody. I'm going to try and take a photo myself. But I think it's not presenting in my screen for some reason. So I'm going to try and take a picture, but I see what's going to happen. I think it's not going to take the picture, but I can take the picture, but when I stop recording. So I'll take the picture later, because right now, take a picture. Yep, and send it to the chat. Very good. Yes, thank you, Ayana. And let's see. Let's take a moment to everybody say hi to your classmates at home. Let's see Camila's work. Camila built the diagram, and she got the same result. So here we have the diagram. And we have the same result. All right, so if you have minus 473, that is the value that we were looking for. Good job there, everybody. All right, let's go back to our presentation. And let's talk about Free energy and entropy, which is the topic that we're going to discuss in this last part of the class. So, free energy and entropy, very simple. We're not going to stick a lot of time into this. Remember, some reactions are spontaneous and some reactions are non-spontaneous. There are some aspects that are going to influence if a reaction is spontaneous or not. What makes a reaction spontaneous? Two important things we need to know for a reaction to be spontaneous. So there's an equation that we use for this, which is the equation that involves what we call the free energy of the reaction. Yeah? So free energy of the reaction, the equation goes like this. Delta G, 0, is equal to what? Delta H minus T delta S. So what this equation is telling us is there's two factors that are going to influence if a reaction is spontaneous or not. When is the reaction going to be spontaneous? When delta G is, if delta G is negative, delta G is less than 0, then you have spontaneous. Right? If delta G is more than 0, then the reaction is non-spontaneous, which also means that the opposite reaction is spontaneous. Right? Now, keeping that into consideration, remember the two important factors that we have here. Delta G depends in both the enthalpy and the entropy of the process. Both factors are important to know if the reaction is going to be spontaneous or not. We have a message from Ayana. Ayana, you sent the pictures. There we go. I found them. All right. So, we're going to know two factors are important to know if the reaction is spontaneous or not. So, what are these two factors? First factor is delta H. If we want delta G to be negative, what would be the best thing for delta H to be? Will it be better that delta H is positive, or it will be better that delta H is negative? Negative. Negative delta H favors the processes being spontaneous. What does negative delta H mean? Exothermic, that's right. So exothermic processes favor the spontaneous processes, right? But that doesn't mean that all the exothermic processes are going to be spontaneous. No. What does exothermic mean? It means that it's releasing energy, and we can imagine if we're releasing energy, that's making the reaction more spontaneous because it's favoring the release of energy and going to a lower energy state. That's good. But there's a second factor, and the second factor is delta S. So delta S, which in terms of if we want delta G to be negative, delta H would be what? Positive delta S favors spontaneous processes. Okay? Now, what does delta S mean? Entropy. And what is entropy? Disorder, randomness, however you want to place it. If we increase the entropy, what we're saying is there's going to be more randomness, more disorder, we sometimes say. So we know that we increase the disorder when we increase the number of particles, for example. When we go from a solid state to a gaseous state, for example. When we go from from less gas to more gas. All these are or when we go to something that is in solid state to it is being dissolved. All this, when everything starts to move more and they have more possibilities, that is going to increase the entropy. That means that if you have a system where the enthalpy is negative, the change in enthalpy is negative, and the change in entropy is positive, that process is going to be spontaneous. However, of course, that also means that these ones are always going to be negative. But this also means that if we have a reaction where delta H is positive, which means it's endothermic, and delta S is negative, then delta G is going to be positive always. So these are the cases that are defined as spontaneous or non-spontaneous. Every time you have delta H being positive and delta S being negative, it's non-spontaneous. But if you have delta H being negative and delta S being positive, it's always going to be spontaneous. What if we have any other combination? Delta H being negative and delta S also being negative, or delta H being positive and delta S being also positive, which means when you have that both processes or both factors have the same sign, what is going to happen then? What is going to happen to delta G?
It
Depends
will
on
depend.
temperature. Say that again?
It will depend on temperature.
That's right. It was going to depend on the temperature. So, in that sense, let's see what cases we're going to have, and we're going to write it down in the table that we often write for this. This is the table that I always write for this. Delta G, delta H, delta S. So we already said, if delta H is negative and delta S is positive, this is going to be positive. If this one is positive and this one is negative, this one is going to be negative. If this one is negative and this one is positive, what can we say about delta G? Is it too dark? Is it difficult to see? Delta G is the first row. Yes, you're right. Sorry. I made a mistake. The first one here is the other way around. Delta G is negative here and positive here. My mistake. Thank you for clearing that out, Camila. These colors are not very nice over here. At home, you see it very nicely, but here in the classroom, it doesn't seem very good. So, now if delta H is negative and delta S is, I'm writing the same thing over again. I'm repeating. So, if delta H is negative and delta S is negative, what is going to happen to delta G?
It's gonna be minus.
Is it always going to be minus, though, Arjan? So remember the equation. The equation, I'm going to write it here at the bottom again, is delta G, it doesn't fit at the bottom. I don't have space. Delta G is equal to delta H minus T delta S. So, if we have low temperatures, which of the two factors is going to be bigger? Delta H or T delta S? Actually, I'm going to do something which is going to help us out here. Do you have a marker, Mr. Raconte? I'm going to use an assistant. Let's see if we can do this. Camila, you're going to be my assistant. Can everybody see me? Not yet. Start presenting.
Yes, we can see.
Okay, very good. So, delta G is equal to delta H minus T delta S. That is the equation. Of course, everything in standard states. Now, one thing that you should remember is that delta H is measured in kilojoules, while delta S is measured in joules. Keep that in mind always. It's important that you remember that. Now, at low temperatures, which one is going to be bigger, delta H or delta S? Well, actually, let me say that again. That is not correct what I just said. At low temperatures, delta H is going to be more important than T delta S. Delta S is always smaller than delta H because this one is in joules and this one is in kilojoules. But when the temperature starts to become bigger, this factor starts to grow and grow and grow. And as that factor grows, then it's going to become more important. At low temperatures, delta H is dominant. At high temperatures, delta S is dominant. Which means that if delta H is negative, it's going to dominate and make the reaction spontaneous at low temperatures. If delta H is positive, it's going to make the reaction non-spontaneous at low temperatures. Delta S, when the temperature becomes higher, at high temperatures, delta S being positive is going to make our reaction spontaneous. And at high temperatures, negative delta S is going to make our reaction non-spontaneous. So this is going to be spontaneous, non-spontaneous, spontaneous, non-spontaneous. This one dominates at high temperatures. This one dominates at low temperatures. So you can combine them. Negative and positive at low temperatures, spontaneous. At high temperatures, spontaneous. Negative and negative at low temperatures, spontaneous. At high temperatures, non-spontaneous. Positive and positive. Low temperatures, non-spontaneous. High temperatures, spontaneous. Now, what happens when delta T and T delta S are equal? If delta G is equal to T delta S, or let me say it in a different way. What happens when delta G is equal to 0? That is correct. Delta G is 0. This is what we call equilibrium. We are at equilibrium when delta G is equal to 0. And when that happens, then 0 is equal to delta H minus, I'm forgetting to write all this, I can't write it, minus T delta S, which means that delta H is equal to T delta S, and that T is equal to what? Delta H divided by delta S. What is this temperature? What is it? What happens at the temperature where delta H, at this temperature we have the delta H over delta S is equal to T? What is this temperature? What happens at this specific temperature? Go back. This temperature came from here. And this temperature came from here. And this temperature came from this. So what is that temperature? This is what we call the equilibrium temperature. At that specific temperature, and that's the only temperature, where delta H and delta S are going to cancel out. I'm missing something else. Now, temperature is going to be measured in what units? Kelvin, that's right. Which means that it can never be negative. Because then thus there are no negative temperatures in Kelvin, right? So, what sign do delta H and delta S need to have for this temperature of equilibrium to exist? Both positive and both negative. So look at it here. If both are negative, at low temperatures it's spontaneous, and at high temperatures it's non-spontaneous. There's a temperature where everything changes. What temperature is that? The equilibrium temperature, right? If this one is negative and this one is positive, at low temperatures, spontaneous. And high temperatures, spontaneous. So where's the change? It's always spontaneous. So there's no temperature of equilibrium. It doesn't exist because it's always spontaneous. If this one is positive and this one is positive, it's always non-spontaneous. So, sorry, no, I said that wrong. If this one is positive and this one is negative, it's always non-spontaneous. So there's no temperature of equilibrium. Okay? All right. Very good. Excellent. So let's go back to our presentation. Thank you, Mr. Ragnajan. Thank you, Camila. So here we have, if I'm doing this right. No, I'm not doing this right. Share screen. What we just mentioned about the entropy of equilibrium, the temperature of equilibrium. This is exactly what we just measured. Delta H is equal to T delta S, delta S is equal to delta H over T, or T is equal to delta H over delta S. What we just said, that is what happens at conditions of equilibrium. Now, how do we know if a reaction is going to be spontaneous? We need to know the sign of delta G, and that's how we're going to determine that. Oops, we're going to run out of battery. So I'm going to move this forward. This is all things that we have already discussed. So let's do a calculation. So just a second, everybody at home, you can see this, but people in school cannot. The reaction between solid barium and solid ammonium chloride can be represented by the equations shown below. So we have barium hydroxide reacting with NH4Cl, barium chloride is formed, ammonia, and water. And that has an enthalpy of 51.1 kilojoules per mole of barium chloride, I guess. The standard entropies at 298 Kelvin for the reactants are given here. So one thing that we didn't mention is how do we determine the entropy change? Entropy change is calculated as entropy change is, thank you, Mr. Ragman. Delta S of a reaction is equal to adding the entropies of products minus the entropy of the reactants. Now, notice that I didn't write delta S of products, delta S of reactants. Entropies are not a change like enthalpies. They are an actual value because of the definition of entropy. Entropy says that a zero entropy is zero. Zero entropy is when we have a crystal in standard state at 0 Kelvin. So that's where we start with the 0. So based on that, let's try to calculate the entropy change of the system, and let's find out if this reaction is feasible, that means spontaneous, at 298 Kelvin. So first part, calculate the delta S of the reaction. So start doing that. I'm going to make the values a little bigger. As big as it gets. Okay, whenever anybody has a value at home, remember to include the coefficients of the equation, you have 2 moles of ammonium chloride and 2 moles of ammonia and 2 moles of water. That is important to keep in mind when you're calculating. Have an answer? 389? 59. 359 is our answer that we have over here. I'm not going to show it right now. We have time.
Mr. Daniel, can you
Yes? Yes? Alisher, were you saying something?
can you show the value of enthalpy change?
Yes, I'm going to show the value. Do you already calculated the entropy? So the entropy, we have it. Here's the value for the enthalpy for the second part. The enthalpy is 51.1 kilojoules per mole.
Okay, thank you.
Okay. 51.1 positive. So we found, and what we're saying here by Ayana and Camila found the entropy change to be, again, can you repeat it for me, ladies? 359.2,
It's
what
spontaneous.
units? Joules per mole Kelvin. That is the
It's
delta
a
that we obtained here.
spontaneous
You have the same value?
Yes.
Yes.
Okay, good, excellent. So now we have the enthalpy. Now the enthalpy is 51.1 kilojoules per mole. Remember that, kilojoules. When we're going to use the equations to find delta G, that is important to keep in mind. So the question is, from this answer A and from the answer C, well, doesn't matter. From the enthalpy that we have given there, which is 51.1, and the entropy that we just obtained, is this process spontaneous or feasible at 298 Kelvin?
It's spontaneous.
What value did you get for delta G?
Minus 54.145 kilojoule per mole.
Minus
145
54.145 kilojoules
kilo per mole.
per mole. Did everybody get the same value? No?
Similar value.
Similar value you get over there, somebody? And here we have different values. If it's similar, the idea is that it's similar. Kind of similar? Okay, so how much did you get, Ayana? Minus 55. Minus 55. I'm going to write both of them. Minus 55.9 kilojoules. I'm going to leave it with 9. I think it's enough significant figures. Mole to the minus 1. Now, that means that at that temperature, this process is spontaneous, 298. Calculate the minimum temperature in Kelvin at which the reaction is spontaneous. We already saw delta H is positive or negative in this case.
Positive.
Delta H is positive and delta S positive.
Negative.
So we said positive and positive means at low temperatures it's non-spontaneous or spontaneous? Non-spontaneous. And high temperatures it's
Spontaneous.
spontaneous. So what we're looking for is the temperature of equilibrium. And since we know that at low temperatures it's non-spontaneous and at high temperatures it's spontaneous, that is going to be the lowest temperature at which the reaction will be spontaneous. How much is that temperature?
143.
Say that again?
143.
103 Kelvin. So again, I'm going to show it for everybody. I'm going to mention it here. If the process has a delta H that is positive, and it has a delta S that is also positive, at low temperatures, delta H dominates, so it's non-spontaneous. At high temperatures, delta S dominates, so it's spontaneous. So there's a temperature in the middle, this T equilibrium, which is the lowest temperature at which the process will be spontaneous. So that's why in the question they're asking us the minimum temperature at which the reaction is spontaneous. Over that temperature, the reaction is for sure spontaneous. Below that temperature, it's going to be non-spontaneous. Okay, everybody, I think we did a good job. It was an interesting way of handling the class today. Participation from both sides, very good. Thank you, everybody, and we'll see each other on Friday, I guess.